This video is going to start our journey into looking at two-event probability, where we might have more than one event occurring and we want to know the likelihood of all of those combined events happening. And so we sort of split this into sort of three sections. This first video is going to primarily focus on and probability. So and probability is looking at, we want to know this first event happens and then it's followed up by the second event. So both events occur, they both happen. Sometimes you'll hear this referred to as and probability. It's also multiplicative, because it uses multiplication. And then within this, though, we do split it into two different sections because we have independent events and dependent events. So if we're focusing on the independent events, what you're going to notice with the independent events is that with these multiple events, the first event does not impact the second event's probability. They are totally separate from each other. A very classic example of this would be flipping a coin. If I'm flipping two coins, the outcome of coin one does not impact the flip on coin two. So when we describe finding this probability, you'll see it written the probability of A and B occurring. And so we would find that by taking the probability of the first event times the probability of the second event. And so if we go back to that coin example, and I'm going back to it because if you remember in our previous video, we went through and we said, okay, here are all of our outcomes of coin flips if we have multiple coin flips, and if we got two heads, there was a 1 in 4 chance of that in theory. Well, we can use this independent events the same way. So if I wanted the probability of getting heads, the probability of the first coin landing on heads is 1 out of 2. The probability of the second coin landing on heads is also 1 out of 2, which got me a probability of 1/4. So notice this is a different strategy to approach the same question we did earlier. So let's look at it in a slightly more complicated situation. We have a roulette wheel here. The roulette wheel is split into 38 slots. 18 of them are red, 18 of them are black, and 2 of them are green. And since we're dealing with green, I'm going to switch my marker to green. Why not? We want to know the probability of spinning 3 green numbers in a row. So notice, yes, we have 3 events occurring here. So even though we titled this page two event probability, that's just to say we have multiple events happening. Now, to do this probability, we need to know the probability of just that first event happening. And so that would be just the probability of getting 1 old green. Well, there are 2 greens and there are 38 slots. So we would say there's a 2 out of 38 chance of it landing on green just once. Now, if I want the probability of 3 greens, that first spin has a 2 out of 38 chance, but then the second spin also has a 2 out of 38 chance, and then the third spin has a 2 out of 38 chance. And so what happens here is we actually have a very low likelihood of this event occurring because of the 18 red, 18 black, and 2 greens, there are sort of 54,872 different ways that I could get sort of a combo depending on my spin. And then, there are sort of 8 of those involve 3 greens. And so that's a teeny likelihood. In fact, if I turn that into a decimal, I would get 0.00014. That is less than 0.1%. So the likelihood of getting 3 greens in a row is almost non-existent. But just to give you sort of a sense of what happens. Now, this would be events where each of those spins didn't impact the previous, weren't impacted by the previous spin. Those are independent events. If I'm focused on dependent events, sometimes you'll hear this called without replacement. like we don't put it back, but the first event we look at impacts the second event we look at. And so when we're dealing with our dependent events, I like to think drawing out of a deck of cards. If I'm dealing out my deck, and let's say, I'm playing blackjack and I put one card down and I notice, I have an ace there. Of the cards that are now remaining, there are only 51 cards left in the deck and 3 aces, not 4 anymore. And so, my probability of what I get next changes based on the fact that there have been cards dealt out already. And so when we deal with this type of probability, if A and B are dependent on each other, our sort of quote unquote formula changes. And so yes, we have the probability of A, but then it's times the probability of B given that A has already occurred. So like given that first event already happened. It might be passing out candy from a bag. I pick out one, Dum Dum, and then I give that to someone, and then I go and I draw another piece of candy. There's one less Dum Dum in the bag. There's one less piece of candy. The odds of what I draw out change. So this also works when sort of selecting people for groups. So we have a 3-person jury must be selected at random, and the pool has 6 men and 6 women. What's the probability of selecting only women? Okay, well, in this particular case, we have 12 total people to choose from. And so what I like to think about when I'm sort of describing this probability, so we have the probability of 3 women, is I'm looking in that first case, the first event, there were 12 people to choose from. But then we've picked a person. So the next person I pick out, there are only 11 people left to pick from. And then, okay, great, I picked another person. So now I only have, 10 people left to pick from. So I've sort of removed a bunch of the possible people that I could end up selecting. Same idea goes then when I'm saying the probabilities. So like, yes, there were 12 people total, and initially there were 6 women total. But now we've picked one of those 6 women, and there are only 5 women left in the pool to draw from. Now, the next one, we wanted another woman, and so now there are only 4 women left. And so notice that each of these probabilities has a different total and a different initial amount because, as we picked more and more people, the probability sort of went down as a group with, it changed. Both numbers went down a little. Now, if I multiply this out, in the top there, I would get, 120. And then in the denominator, I would get 1,320. And so there's my unsimplified fraction. Yes, that simplifies to 1/11. Typically with probability, your textbook's going to ask you to simplify. I like them unsimplified. It's sort of your call. And then as a decimal, if I put this in my calculator, I would actually get 0.0909, and it sort of keeps going. We're going to typically round to the 3rd decimal place this lesson. And so if that's a 9, I'd actually round that to 0.09, and then that 0 is going to become a 1. And so there's sort of my decimal. About 9.1% of the time, we would randomly select an all-female jury. And so dependent events, that first selection impacted the second selection is a really good way to think about it. Would the chances of the event occurring change? Then it's a dependent event. Should the chances not change, then it's an independent event. Hopefully this sort of gives you a sense of what do we do when we're looking at multiple events occurring and we want to know what's the likelihood of all of these events happening.